Hi folks, so we're back in the lab here in 255 Holroyd. Here we go. And this time around we are talking about module 1D, as in delta, acceleration vector in 2 dimensions. So we're going to introduce it a little bit, and then I'll ask my future self to pause it, and pause the video, and then describe what we're talking about mathematically. And then I'll try to explain what we're going to do with the setup, collect some data, and then we'll see how well the mathematical models, the mathematical equations, predict what we see inside the lab. And then we'll also see how well the lab data agrees with the predictions. So it's both sort of a two ways. I'm looking at this thing right now. So what we're going to do is I'm going to put this guy down over here and go back to what we had before. So here are our parts again. These are sort of the parts that we've had before. We did this last time. We were measuring position and measuring velocity and measuring acceleration. And I mentioned that we could possibly use our ping pong ball here to simulate a motion across the room, and perhaps like an angry bird going from one side to the other, or one side to the other. But what we're going to do today is sort of like what we talked about last time, when we, instead of using the ping pong ball to do the drop from 2 meters, again, here's our meter stick, and there's 2 meters in red. It's about 2 meters. Instead of measuring how long it takes for this thing to fall the whole way down from there to there, again, we could do this. This is the last time. I'll see if I can chase this across the room. 3, 2, 1, go. It falls down and it bounces. We can measure the time it takes to go from the red tape the whole way down to the floor and hit that. And by doing so, we can calculate the acceleration of the ball. Okay, it changes its velocity. It's definitely not moving it all up here. I'm holding it. And then it starts to change its velocity. It gets faster and faster and faster and faster and faster. And we now know that that happens to be a constant acceleration. And yes, we'll be talking about gravity here in a little bit. But right now we're just talking about the effects of gravity on the ping pong ball. So it turns out that'd be great if we could measure what that acceleration is. And of course, like I mentioned, the acceleration right now is the acceleration due to gravity. But instead of putting it on this on the rail here like we did last time, what we can do is we can take the rail and we can move it horizontally. So now it's flat. And of course, as soon as I do this, it's not going to work. If I make this perfectly flat, then it won't roll. But if I go ahead and change the angle so that it's not horizontal, the ball will roll in the direction of gravity. So if I change it back over here, it'll roll back. I know this is going to turn out really, really poorly, but I roll it back this way. So all I'm doing is I'm changing the angle with respect to the ground. I'm changing it from being horizontal. And whenever I change it from not being horizontal, the ping pong ball does not stay where it's supposed to be, and eventually it falls off like I suggested. And if I put this up here nicely and it doesn't fall, it won't scare me. Fantastic. I have to go find the ball. Thank you. This is what we did last time, is we actually put one of these rails on the board here, or on the table. And this time around, if I take this ball and I go ahead and put it on the rail there, let's see if it moves. It moves up. It looks like our guy's a little bit not level. So it looks like perhaps the feet down here are too high. I think that's them right there. And again, this is the adjustable feet that we have over here. They're like this. So what they do is I just adjust these guys up and down. So let me go ahead and adjust these guys back and forth. Let me see what's going on here. I'll put these guys back down a little bit. And then I go ahead and put the ball on top of there again. And let's see if it stops rolling either direction. And yeah, it seems to be a little better. So now it seems to be flat, which is pretty awesome. So if I were to take the cart, which we had last time, and I were to set it there, it's not going to roll. But if I were to give it a shove, or if I were to give it an acceleration, last time we gave it an acceleration with the fan, again, keeping my fingers out of the fan. We turn this on, and notice that when this is hitting the GoPro camera, you hear the wind hitting the microphone. It's a lot of wind. That push causes this guy to accelerate, much like if I give it a shove with my finger, it will accelerate it as well. But me shoving it with a finger is not very reproducible. Moving it with the fan is much more producible. But what we're going to do is, remember last time I had the magnetic bumper on the end of the rail. That was this guy. And of course, this guy has a magnet, even says caution magnet, and I replaced it with this guy. But now we're using this accessory, and this accessory bracket happens to have a stiff spring on it. So very similar to the ping pong ball bouncing off of a hard surface, now my cart can bounce off of that spring. So let's see if that works. So it just bounces back, and that's fantastic. Wonderful. So the reason why we're doing this is instead of using the cart fan to give it an acceleration, and instead of me giving it a shove to give it an acceleration, because I can't guarantee that I shove it the same way, what we're going to do is we're going to use this bounce as an acceleration. So what's going to happen is the cart is going to start up here. I think we start in the description around 30. It's going to roll across the cart, and then it's going to bounce off of this and then bounce back. And that is going to be our push, if we will. We're going to use the push of the spring to shoot it back. That's very similar to putting an Angry Bird inside of a slingshot, pulling the slingshot ribbon back and then letting it fly. The slingshot acts like a spring and shoots it forward. So this is sort of the Angry Bird experiment, but it's sort of the Angry Bird experiment in backwards. So if we were able to load this spring, I can't really do this, and then put the thing there and then let it fly. Of course, if I could, it would shoot the ping pong ball. That's what we're sort of doing. So we're going to bounce this guy off of it. But what we need to do is we need to have a component of the acceleration. We talked about components a little bit. Horizontal is exactly that, the horizontal component. And vertical is the vertical component. But if it's slanted, if this rail happens to have a little bit of the horizontal characteristic, well, in this case, a lot of bit of the horizontal characteristic, and a little bit of the vertical characteristic, then a little bit of the acceleration will be part of the force, or part of the gravity that's pulling this thing down. And of course, the way we're going to do that is we're going to tilt this rail, just like I was tilting that rail, but over there I was tilting it, just sort of holding it. Here we're going to tilt it, quote unquote, scientifically, but just for a check, if I were to tilt it by just holding it like this is not how we're going to do the experiment, and I give it a shot, okay, this guy now has a tilt. It now has a component of acceleration, and it will bounce, if you will, off of the spring. The data that we're going to collect, we'll collect the whole data as this thing runs down the rail and then bounces off the spring. But the data that we're interested in is the data after the bounce. So it's going to roll down here. This is just me pretending. It's going to roll down here. It's going to squish the spring. The spring is going to shoot it back up as if it was being tossed. So now I'm tossing it against gravity in this direction. It'll rise to the top, it will stop, and then it will turn around and then come back down. That's the data we're interested in. We'll collect a whole bunch of data, but then we're able to select what data we'd like to analyze inside the software, which is kind of cool. So what we're looking for is we're looking for the data of being shot away from the spring, coming to the top, if you will, of the slope or the slant, having it stop, and then having it fly back down. What that will allow us to do is it will allow us to measure the acceleration in this direction along the track, and then we can calculate that, and we can measure it, and we can compare the two to see if our equations are working pretty well. Fantastic. So what we want to do is come back over here to this guy and see what's going on. So yeah, this is us. Background, again, here's a Here's the stuff that we'll talk about in the future. Me will be talking about this actual diagram to determine how much of the down acceleration due to gravity is now a component of this direction along the track. That's kind of cool. And the way we're going to do that is we're going to measure the tilt angle. We're going to measure how much of the track. If it's perfectly horizontal, the tilt angle will be 0. And if it's not perfectly horizontal, then hopefully the tilt angle will increase until the whole thing is 90 degrees. Now, if it was 90 degrees, what we get is that guy. So if I take this particular rail and I put it against the wall, and I hope that the wall is not leaning, then that's 90 degrees. And pretty soon, it's pretty obvious, if I take the cart, I'm not going to do it, and put it up here, it will fall as if it was accelerating to the rate of gravity, the same way that the ping pong ball fell at the rate of gravity acceleration. But we're not going to do that. We're just going to use a smaller version of that. So let's follow what this guy says, and we'll see if we can get this guy to work. So we're back over here to the computer. The computer's all set up, okay? Attach the motion sensor to the 0 meters end of the 1.2 meter track system. That's done. Extend the feet on the foot bracket closest to the motion sensor to their maximum setting and retract the feet of the foot bracket on the other side to their minimum. So that's what we did. So this is already minimum down here. Again, what we want to do is we want to intentionally tilt this. And if we tilt it, then everything will have an acceleration in this direction, and that's what we want to measure. So we're going to go ahead and do that. I'm going to grab this foot down here. And sorry if I'm making everybody dizzy by moving my head with the GoPro, but I'm going to bring this guy down. It just needs to be arbitrary here. Bring this guy down pretty far. There we go. Alrighty, is this working? Make sure it's level side to side. Fantastic. And bring this guy up a little bit. Oh, I knew that would be the case. I opened them so much that I have pulled them out. That's usually what happens. And then I put this guy back down again and not on the table. Okay. Now, to measure this, we're going to use a really, really expensive angle indicator. I have another one over here. It is also provided by the Pasco people. They love their logo. And as you can see, what this guy does is it takes a little tiny lead ball on the end of a string. It's called a plumb line. I wonder why. It's called a plumb line, not P-L-U-M because of the fruit, but P-L-U-M-B because of the lead hanging on the end of the line. It turns out that Pb is the symbol, chemical symbol for lead, and plumbium, it happens to be its Latin term. So a plumbium or a plumb line just means, hey, take a string, throw it over the side, and gravity will always point it down. So no matter where I move this, if you can see that, gravity always pulls it straight down. So it's a gravity indicator is what it is. It says angle indicator. So now we've attached this to the track, and if the track is tilted, then the angle indicator, the gravity indicator, will tell us at what angle the gravity component is now pushing. So let's see if we can go ahead and grab that over here. If I get my pen, if I look at this, I can look closer. Here we go. It's really hard to see, obviously, but it sure looks like it's sitting about 1 degree. Okay, it's moving a little bit. Let's call that 1 degree. We don't need that much significant figures. So over here in my data section, I'm going to go ahead and move this guy back here and say the first time around the tilt angle happens to be 1, get this guy down here, 1 degree. That's cool. We don't need a lot of sig figs for this guy to work or not work. That's page 7, this is page 3, and this is page 6. Fantastic. 3 and 4, there we go. We're back where we were. So now that we have the angle, let's see if we can't get this guy to work, okay? Plug the leads of the motion sensor into the Pasco interface. We've done that. So here's the motion sensor into the motion sensor in the Pasco interface. This guy, that's lead 1 and lead 2, the yellow one and the black one. Double-click Data Studio icon on the Windows desktop and open the application. Sure thing. So I go over here, And we're good. And I open up Data Studio, double click it, and we launch Data Studio, and that's fantastic. I close this. And then it says to go ahead and the software should indicate select the Science Workshop 500 interface and select OK. So we need to tell it that this box, this model of this box is connected. So I go to Experiment and I go to Change Interface and I tell it the Science Workshop 500 is connected and I say OK. And it looks for the interface, it found it, fantastic, it initializes it, and we are good. Wonderful. In fact, there it is sitting up there. That's fantastic. All right, last time we used this software, we just went ahead and went File and opened an activity. This time around, we're actually going to go ahead and add this motion sensor to the box, and then we're good to go. It's pretty easy to do, so we're going to do that. Let's see here. The software should indicate it's found it. Wonderful. Display the Science Workshop digital sensors by selecting them from the drop-down menu. Okay. So over here it says add sensor or instrument. So I go ahead and click on this guy. And right now it's reading Science Workshop analog sensors. And of course an analog sensor outputs voltages that are like between 1 and 5 or 1 and 9 depending on how they work. We want the digital sensors. So here we go, digital sensors. And of all the digital sensors that they sell, the motion sensor is one of them. So here we go. We say OK. And then what it's going to do is it's going to add the motion sensor, this guy, to our box. And you can see right here, it's a little tiny picture of a yellow plug and a black plug. And it's pretending to show that they're plugged in there. It doesn't show you an actual picture, but it's close enough. Fantastic. We're going to click on the motion sensor tab near the bottom of the dialog box. Down here it says motion sensor. Okay. And you'll hear that this guy is doing this old tick. Again, what it's doing is it's sending an echo pulse down the rail, waiting for it to echo off and then coming back and then recording that. So right now it is telling us that it's sitting at 1.951 meters. And what we want to do is the standard distance is 1 meter. So I'm just reading this answer. What we're going to do is we're going to